Salam sejahtera and good day to our lecturer, Dr. Adia, and my fellow friends. Hello, my name is Yap Zishan and I'm from 2 BEKG section 4. So today we are going to talk about our topic for assignment 1, which is capacitance parallel plate. So first, capacitance of two conductors is defined as the ratio of magnitude of total charge on either conductor to the magnitude of the potential. So in general, this definition can be summarized by this general equation here, which is C equals to Q over V naught. So next, as we can see here, there's two parallel plates here. The first plate is positively charged and the second plate here is negatively charged. The electric field flowing from positive to negative. So C equals to Q over V naught. We'll sub in the two Q and V general equation, and then we know that D electric flux density equals to epsilon naught times by electric field. So we'll sub this D into the E here and we'll get something like this. Next, we know that electric field equals to rho s over T epsilon naught plus rho s over 2 epsilon naught. So you may ask why there's 2 rho s over 2 epsilon naught here. This is because the first electric field is produced by, there's two electric field actually. One is produced by the positive plate and another one is produced by the negative plate. So we work it out and we'll get E equals to rho s over E z cap. Next, Q equals to epsilon naught times by integral rho s over E. We sub this E into the Q equals to epsilon naught cos integral of E, and we work it out, we'll get Q equals to rho s times by S, where Q is charge and S is the surface area. So lastly, we work the V naught out. V naught equals to negative integral of negative to positive E dl. We know that the distance between the positive plate and the negative plate is D. So we sub D inside here, we work the integration out, and eventually we'll get V naught equals to rho S over epsilon naught times by V. D is the distance between the two plates. So now we get Q and the V already. So we sub Q and V naught into the C general equation, and eventually we'll get C equals to epsilon naught times by surface area over D. The S will be the surface area while D will be the distance between the two plates.
Hi, my name is Paul. Today I'm going to present question 1. So in question 1 we have 4 sub questions with A, B, C and D. Further ado, let's move on to question A. Question A is to apply Gauss law on capacitor parallel plate to show the electric field between the plates. So we need to find the E lah. So first thing we need to draw the diagram first, and we assume the Gauss law apply the Gauss law using a cylinder, something like that, and we'll place the cylinder over here. Okay, and the electric field for this is facing out also, so it's parallel to the capacitor plate. So by using the Gauss law, we'll get integration E times dA equal to charge over epsilon naught. So we integrate dA, E times dA, you will get dA because the E here is parallel with the A, alright, and will equal into charge over epsilon naught times the A or the ratio of area, which is the area of a cylinder over the area of the capacitor AC. So you get this equation here, then you cancel out the A. You do math, right? Then you get the electric field, something like this. Then you get the full marks. Move on to question B. Question B, obtain the expansion of capacitance of parallel plate capacitor with air field in between. As usual, draw the diagram first. The diagram can give you a better understanding and also easier to explain and get marks. So we need to get the expression of capacitance, which is C equal to Q over V. So Q we know is charge. We need to find V. The V formula is V equal to E times dl, which is differential length. Okay, so you you find E. E, the equation is equal to, over here, is sigma over epsilon naught. Sigma is the surface charge density. Okay, so we replace the E to sigma over epsilon naught times D. Why is D? Because D differential length, you get L. L over here is D. So you replace it with D. Then what is sigma? Surface charge area. Surface charge area density is charge over the area. So we substitute into this equation here, over here. Right, then you substitute this v into this. So you get this equation over here. Then you do the math also. Charge cancel out. Then in the end you get this equation. Okay, that's all for me. Thank you.
Hi, my name is Ojuti, and I will explain about the question 1C and D. For the question 1C, what is the capacitance of a parallel plate capacitor with metal plates, each of area of 2 meters square separated by 1 millimeter? And we use the equation that expressed from the question 1B, which is C is equal to epsilon naught times A divided by D, which A is area and the D is the distance between the parallel plate capacitor. The epsilon naught is 8.85 times 10 to the power of negative 12, and the A is 2 meters square, and the distance between the parallel plate capacitor is 1 times 10 to the power of negative 3. And we will get the capacitance of the parallel plate capacitor is equal to 17.7 nanofarad. This small value for the capacitance indicates how difficult it is to make the device with a large capacitance. Special techniques help, such as using very large area, thin false plates close together. Last, for the question 1, what charge is stored in this capacitor if a voltage of 5 times 10 to the power of 3 watt is applied to it? For this question, we use the equation for charge to the capacitance, which is Q equal to Cv, which C is equal to 1.77 times 10 to the power of negative 8, and V is 5 times 10 to the power of 3. And we will get the charge, which is 88.5 microcoulomb. This charge is only slightly greater than those found in typical static electricity, since it breaks down at about 5 times 10 to the power of 6 V per amp. More charge cannot be stored on this capacitor by increasing the voltage.
Hi, my name is Lu Wei Jun, and today I will present question 2 for capacitance parallel plate. So this is question 2, we got A, B, C, D, E. So for question 2a is define capacitance. So what is capacitance? So from the formula we can see that capacitance is equal to charge over voltage. So the answer is capacitor can be defined as charge on a plate divided by voltage difference. This is question 2b, and the question is parallel plate capacitor has a capacitance of 40 microfarad and has rectangular plates with 80 cm times 40 cm dimensions. So we need to calculate the space between the plate. So the equation for parallel plate capacitor is C equal to epsilon naught times A over D. So C is capacitance and epsilon naught is electric constant, while A is equal to area of plate and D is space between the plate. So from the question we know that C is 14 microfarad, epsilon naught is 8.85 times 10 power of negative 12, and A is 0.8 meter times 0.4 meter equal to 0.32 meter. So what is D? So from the formula, D is equal to epsilon naught times A over C. So D is equal to 8.85 times 10 power of negative 12 times 0.32 over 40 micro. So the answer is 70.8 nanometer. So that's all for my present. Thank you.
Hi, my name is Tan Hong Yi. Next, I will continue with question 2C. So for C, the question asks to calculate the electric field inside the capacitor. So the equation used is E equals to V over D, while E is electric field, V is voltage, and D is space between the plate. So D is 70.8 nanometer, V is 30 volt, find E. So E equals to 30 over 70.8 nano. Then E is 423.72 megavolt per meter. Next, D. If the capacitor is connected to 30 volt battery, calculate the charge on a plate. So, equation for charge on capacitor plate is C equals to Q times V. Q is charge on plate, C is capacitance value, and V is voltage. So from the question, we know that C is 40 microfarad, V is 30 volt, find Q. So the formula we use is C equals to QV. Q equals to C over V. So Q equals to 40 micro divided by 30, which is 1.33 microcoulomb. Last question, E. If the same capacitor is connected to 80 volt battery, will the capacitance increase, decrease, or remain the same? Explain. First, equation used is Q equals to C divided by V. Q is charge on capacitor plate, C is capacitance, V is voltage. So by observing this equation, Q is inversely proportional to V. So as voltage increase, charge will decrease in the condition that capacitance remain the same. So the next equation is C equals to epsilon A divided by D. So C is actually depends on epsilon A or D. C does not depend on voltage. Thus, capacitance will remain the same as voltage increase. So that's all from our group. Thanks for listening to our presentation.